Good morning, everyone. Nice to see you back. 9 o'clock we start. So today we have second part of the lectures by Marco Vignati on solid state detectors. Then we move to liquid scintillator in the morning, water challenge in the afternoon, and the last part of the statistics class and so on. Tonight we'll have the social dinner together at l'Académie, the House of Wine. So, Marco, thanks.
Thank you. So we continue from yesterday, and we reviewed these experiments, ionization detectors, CCDs, light and crystal. We talked a lot about gamma, and today we talk about phonons. So different sensors, entities, chips and T-axis, experiments, Quarry, Crest and Burgit, and also Ricochet, which share the technology between phonons and ionization. So, when do we have to use phonon detector, meaning cryogenic detectors? Well, not always, and maybe we should not do it so often because they're very difficult detectors to operate, but we need them when we really need the ultimate sensitivities of detectors. So we have seen semiconducting detectors, the principles, and we have seen that even if you have a band gap, which is order 1 electron volt, you need to provide to the system an energy which is a factor of 3 to 4 higher in order to create an excitation. So there is an energy loss, which is basically the 70% of the total energy, which is not visible in the ionized charge channel. And this energy goes into heat. So if you want to measure all the energy and improve our energy resolution and lower the energy threshold, we need to measure the entire energy which is carried into the system. This means that you are forced to measure the heat of the released in the devices. So the working principle of cryogenic detectors is that of an ideal calorimeter. So you have an absorber which has some heat capacitance. When particles release energy in the absorber, the temperature of the absorber increases proportionally to the energy. So the absorber is thermalized at low temperature. Typical temperature are from 10 to 100 millikelvin. And we need sophisticated temperature sensors in order to sense the small amount of heat which causes the temperature increase of the absorber. Just to give you an idea of what you can gain with this method, so if the energy resolution is proportional to the square root of the energy of the quantum and of the energy released in the system. So for semiconducting or scintillation detector, we are on the order of 1 electron volt for the quanta, while in the case of cryogenic detectors, the quanta are the phonons, and the energy of the phonons at temperature T is kT, and if you plug to 100 millikelvin, this gives you 10 microkelvin, which is to be compared with this. So in principle, we have no limit in improving the energy resolution and make it as small as we want. And let me repeat, so in this case, we have the quenching because the energy is lost in the excitation. In this case, we have no quenching because we always measure the full energy which is released to the system. Even if this is a semiconductor, so if you then excite and you create ionization, in cryogenic detectors, you can wait long enough such that the electrons all recombine, and again you get heat back. So we can convert also this amount of energy into heat. So in total, we always have heat. The the drawback is that being these are purely thermal detectors, they are much slower than these detectors, but this is not a concern for experiments searching for rare events like dark matter, double beta, or neutrino interactions at low energies. So cryogenic detectors are used in many fields. I would say that the most successful fields for this kind of detector is cosmology and astrophysics. So the Planck satellite, which measures the CMB spectrum very accurately, use cryogenic detectors in order to sense the 100 gigahertz wave of the CMB. The crest dark matter experiment, which is at Gran Sasso, the core experiment on double beta decay, but they are also used in for solid state applications to get very precise measurements of X-ray spectra. So just one slide on how do we reach low temperatures. So cryogenic detectors usually refers to very low temperature, so well below 1 Kelvin, 100 millikelvin, 10 millikelvin. And so going down from 300 Kelvin to few Kelvin, that is not such a challenge because you can use liquid helium, which per se gives you 4 Kelvin of temperature. And then by playing a bit with the pressure, you can easily reach a few Kelvin, 1 or 2 Kelvin. The more interesting part is that goes from a few Kelvin down to fraction of Kelvins. And this is achieved with a mixture of gases, which are two gases, one made of helium-4, which is a bosonic gas, and helium-3, which is a Fermi gas. So when we cool the temperature, these two gases undergo a phase separation. So we have a normal fluid, helium-3, helium-4, and then here we start with superfluidity of helium-4. So here we have a post-condensate. And below this temperature of 0.27 Kelvin, we have a phase separation. Okay? So we cannot access this region here, or we are here, or we are here. So we have a fraction of the fluid which will be here, and the fraction of the fluid will be here. And these two fluids will be separated. One is much richer in helium-3, and the other fluid is much richer in helium-4. So usually this stays below because of gravity, the helium-4, and this stays above, which is more helium-3 than helium-4. So you have these two fluids, one on top of the other, and then we add some work from the outside. We can pump helium-3 gas through the helium-4 condensate, so meaning that we bring helium-3 from here to here, and this gives you also this lowering of the temperature, because the evaporation of the helium-3, which is contained in helium-4, is a process that absorbs heat. So with this mechanism, thanks to the work of an external pump, this work is converted into a temperature lowering. And this can achieve temperature also below 10 millikelvin. The point is that this gas here, helium-3, is very costly, so we can use only a small amount of this gas, because this gas here, so 1 liter of gas at standard temperature and pressure can cost up to $5,000. So this is not something that you can scale up to any volume. So here's a picture of our lab at Sapienza University, just to show how cryolab looks like. So this is the cryostat. In this case, is closed. So this is the fridge, basically. So the system that brings it to low temperatures. And this is the same fridge once it's open. So once we remove we are at room temperature and we open the vacuum. And usually the working volume, so I mean the experimental volume where you can put your devices or your anything that you want to cool down is of the order of few liters with commercial cryostats. And what you see around, this is the just gas handling systems and the electronics for the devices. And this is the control unit of the cryostat. Thanks to the development of the quantum technologies in the last years, so these systems become quite diffused. Now the market is quite large, of the order of hundreds of these systems per year sold worldwide. This means that also these systems became much easier to operate. When I started my PhD, it was quite difficult to operate one of these machines, so you really need some expert that knows all the magic of the system. But now it's like they are more like a laundry machine when you push a button and then it goes down to temperature. So this is also easy a lot the operation of this kind of devices, which otherwise most of the time you would have to spend the maintenance and trying to keep the machine working. So we can divide the cryosensors in two classes. Well, I like to divide them in two classes. One is high impedance device and the other class is low impedance device. So high impedance devices are the most simple to operate because basically they are resistors in which you have the resistance, then we will see how these are made. So you have a resistance that has a strong exponential dependence on the temperature, and therefore this device works as a thermometer because you convert temperature variations into resistance variations. So in the end, you need to measure a resistor, and your signal will be proportional to the resistance of the systems. So with these devices, depending on the application, this is an application for X-ray physics, you can reach very good energy resolution, 3.2. In this case, we are at 3.2 electron volts per critical maximum at the iron lines of 6 kV. But being a high impedance device, we cannot implement any kind of parallel readout. On the other side, there are the low impedance devices, superconducting TSs, and kinetic inductance detectors. So here we have an example. We will go into get into this of a TS, which is again a system made of a superconductor in which we convert temperature variations into resistance variation. But in this case, the scale of the resistance is completely different. Here we are on the order from megaohm to gigaohms. So these are very high values of resistance that we have to measure. In this case, we are in the range of milliohm, and the variation can go down to microohms. So in this case, the resistance that we measure is very, very small. And the kinetic inductance detectors, which are not thermal sensors, but they are cryogenic sensors. So let's start with the semiconducting thermistor, which are the first. So what I said in this order is that we basically also how the community started using these devices. We started with thermistor, now we are with the TESs, and the future is the heats. So this is what comes from cosmology. So these are is the field where these devices as the majority of the application. So now on the Planck satellite, we have thermistors. the next satellite will implement TESs, and the R&D now for the next satellite is on kinetic inductance detectors. So semiconductor thermistors. So these are basically for our application semiconductors. Which can be silicon or germanium. What we use mainly are these germanium pieces of semiconductor in which we have some doping, again, impurities, which are needed to tune the value of the resistance of the semiconductor. Because basically this is a semiconductor, but we want to make it much closer to a conductor. So we create a controlled number of impurities in order to obtain the value of resistance that we want. So when we go to, well, the semiconductor gap, we already seen this is of the order of 1 electron volts. At room temperature, the mean excitation is 0.03 electron volts, but as I remind you, this is a black body distribution, so this means that you can go also at states that have energy that can excite this one. But when you go to much lower temperatures, so 10 milli or 100 milli, you basically don't have excitation from the temperature. And the conduction can only go from one side to the other of the lattice through this tunneling mechanism, which is called hopping conduction, means that the electrons hop from one side to the other side. So there is a model for this way of conducting with electrons, and basically this empirical model gives you this dependency of the resistance from the temperature, which again is this exponential behavior. So we have to measure resistance. So measuring resistance is quite easy. We know how to do it. If, for example, we use the parameters of the thermistors which are used in the Quark experiment, which are this one, we get that the 10 milli, which is the operating temperature of Quark, we have 100 mega ohms. So this is our resistor, which basically is our sensor. The sensor, when energy is released in the system, the value of this resistance changes. And to convert this to a voltage signal, which is what we want in order to acquire the data with our ADC and our computer in general, we have to convert it to a voltage. So how do we do it? So the idea is to go with a constant current excitation, meaning that we have a constant bias voltage with a load resistor which is much larger than this resistance. So this means that the current that flows into this circuit is dominated by this resistor. And when we have this change of resistance, the current basically does not change. What changed is the voltage, because the resistance is changing. So in this way, we have a voltage signal which is directly proportional to the value of the resistance. Then the voltage is amplified, filtered, and digitized as usual. So I'll give you one example of these devices, how they're used in our field. So this field, this experiment is the Quark experiment. So what we had in the Quark experiment is the unit of the detection unit of the Quark experiment consists of an absorber crystal of 750 grams. So again, these are quite big objects, and they are similar to the diode of Gerda. When energy is released in the crystal, we have pulses, temperature pulses like this one. So this is a pulse with energy of around 1 mega electron volts. And so what we have is an increase with respect to the bath temperature of 10 millikelvin of 100 millikelvin for 1 mega electron volts. So we have to sense very small temperature changes. And as said, the drawback of these technologies is that being this a thermal system, it is also very slow. So you see that the time development of the signal can last up to a few seconds. But again, if you're looking for a process that possibly don't even exist, this is not a problem because you don't expect so many pile-ups. So these crystals are tellurium dioxide crystals because again, in order to have a high temperature increase, you also want a low heat capacitance. So you have to choose compounds that per se has low heat capacitance, and usually compounds that are dielectric and diamagnetic have low heat capacitance. And they, being so sensitive, they provide very good energy resolution of order 5 kV fluid maximum. This value is similar or even worse with respect to the one of diodes. So this tells us that even if we are using cryodetectors, the ultimate source of noise is not yet the one due to the statistics of phonons. In this case, we are dominated by temperature instabilities and noise coming from vibrations of the system. Because one of the problems of this device is also that vibrations are an issue because vibration converts to heat, and so they are a tremendous amount of noise. But with respect to diodes, the advantage of this technique is that whilst in the case of diodes you can only use germanium or silicon, in this case you can use you have a choice, much wider choice of compounds that you can study. So if you want to move away from germanium and silicon, you have to go with the cryodetectors. So Core wants to study this process that we have already seen yesterday, so the double beta decay. This is the very same slide of yesterday. And so this is a long story that was started by Professor Fiorini in Milan. So from the 90s, they started with a small crystal, only 70 grams. And this is the development of this technique, which was quite impressive. So here you have the mass in kilograms versus the here. And now we are here, well, now this is since 2015, because this is an experiment that is taking data since 2015, still taking data. So this, from the point of view of the technology, Core has been a great success because it is the largest cryogenic experiment in the universe. And it's also said to be the coldest cubic meter of the universe, known universe. And yeah, it's a total active mass of 740 kilograms for a mass of isotope under observation. This is the isotope that can undergo double beta decay, about 200 kilos, and a background of 10 to the minus 2 kilogram per counts per ket per kilogram per year, which is now the main issue of this experiment, because if you remember, the legend experiment has 10 to the minus 4. So this is 2 orders of magnitude larger than the direct competitor like legend. So nevertheless, so we were able to pull down this such a giant amount of stuff to 10 millikelvin, because this dimension is about 80 centimeters, so 80 centimeters and 18 centimeters. So this is the Core array before pulling down, and this is the result of the Core experiment, which basically gave us, so this is the energy spectrum, this in this white, light yellow, which is, so here we don't have the capability to do fine pulse-shape discrimination like in legend, because we only measure the temperature increase of the crystal, so we don't have any information on deposition like as we have seen in legend, where you have a non-uniform field lines that gives you delayed signal depending on the position of the interaction. So here the pulsation basically is not that effective. However, this brings us to quite a good result. However, as you know, no result because no one has yet observed the double beta decay. Okay, so sometimes we want to even further increase the sensitivity of these devices. And this is a technique which is called the Yukhneganov amplification, which is now becoming quite often used in order to further increase the amplitude of our signals in cryogenic detectors. So how does this work? So the idea is that you need, again in this case, a semiconducting absorber. So this works when you have a semiconducting absorber cooled to low temperatures, and you are sensing the phonons in the semiconductor. Okay, so you apply a bias voltage of tens to hundreds of volts to the system, and what happens is that when an event creates electron-hole pairs, these electron-hole pairs are accelerated by the electric field between these grids. So these electron pairs therefore acquire an acceleration and energy, and then they impact with the lattice of the crystal. So in this impact, there is energy in the form of heat. So this is a way of amplifying the heat signal so that we can convert the voltage given by this constant voltage into extra heat. So you don't only have this, the energy which is released by the particle, but since E over W is the number of electron pairs that you create, these are then acquired the energy from the electric field. And so this gives, which in then through collision is again converted into heat. So this is a way to have basically increase the signal quite effectively, up to a factor of 10 to 20, this works. And for example, if you have to do, for example, a light detector, cryogenic light detector, this is very effective in order to increase the energy resolution of the device. However, so beware that when you use these systems, this is you lose, if you look for nuclear records with this system, you lose what you gain from a cryogenic detector. So the fact that now the signal is dominated by the component of ionization, of the creation of electron hole pairs. So if the signal at the beginning is ionization. So again, you have the problem of electron hole recombination, and the quenching factor applies. So it is just ionization that you convert into heat, but the primary signal is ionization, therefore you do have the quenching factor. So a good way of using this Neganov loop amplification and ionization is as implemented by Ricochet, which is the last of a series of experiments which was developed in France, in which they have a germanium detector, which in this case is not a diode. It is a crystal of germanium, in which the what you can see here are all these the lithography of these wires, which are basically the wires that are used to apply the electric field. And then there is also a temperature sensor on it. So in this way, you can have a double readout. You can read the heat on one side, and then you can also read the ionization. So this is the Ricochet experiment that employs which is employed to search for the coherent and elastic neutrino scattering that we have already seen. And basically, they use the ionization energy, basically, okay, in a correlation with the heat energy, because this allows them to do a very good separation between electron recoils and nuclear recoils. So this ionization signal, in this case, is read directly as ionization signal, but in principle can also be read through the nuclear effect as an increase of the heat signal. But it's good to have them separated because this gives you the identification of a band of nuclear recoils and electron recoils down to heat energies. In this case, this is not quenched because this is measured through an MTV, down to 100 electron volts, which is very good. So 100 electron volts nuclear recoil, you do have the separation between electromagnetic and nuclear recoil events. You have questions so far? So this completes the part of the NTDs. Yeah.
I was wondering about the background. What is the large part of the background in these kind of detectors?
In which experiment? Well, this is compared to which kind of detector you are thinking?
I'm thinking of germanium diodes at the moment.
Okay, so if you think to germanium diodes, well, there's not much difference in this case because the setup, as you can see, is not that different. So you have a structure which is made of copper. So you usually have the same problem in getting a ultra pure copper without low content of uranium and thorium. You have the problem of alpha particles because basically with this device you do not disentangle between surface and bulk events. You don't have a way to disentangle between them. So usually alpha interactions are surface events, and some devices can get rid of them. In this case, you don't have this distinction. And but for the rest, it's the same backgrounds that you have with German diodes.
You said you can't distinguish between surface and bulk events, so this full shape discrimination you can do with the germanium, with the shape, this doesn't work.
No.
So it's like in the edge region is the.
You measure the mean temperature of the crystal, so this is the signal, and you don't have a way to point to some direction with this method. So even if you put multiple thermometers, this is so slow that before that the signal develops in the thermometer, or then the temperature change already involved the full crystal. So the speed is so low that you don't have access to position information.
Other questions? So I have one question. So you mentioned this ricochet. If I remember correctly, there are also some other detectors for dark matter that uses this double channel, the bolometer and the ionization channel, like CDMS for a device.
Yes.
In particular, CDMS uses this Luke-Neganov approach. Basically, they have two ways to run the experiment and correctly. So, playing with the high voltage, they can have good discrimination or good resolution. Can you elaborate a bit on this?
Yes. So the point is this one. So if you this is how super CDMS works. Okay. So in order to have better energy resolution, they increase the signal. So the noise stays the same, and then increase the signal height. How do you increase the signal height? So the heat signal, you do it with this voltage here, which accelerates the electron hole path. In this, the devices are all silicon or germanium. They have two kinds of devices. Maybe now they focus only on one technology, but they still silicon germanium. So if you this is exactly my comment. So the fact is this, that, okay, you want to reach the lowest threshold possible, but this is an KEE threshold, because this is just due to the fact that you are amplifying the ionization signal. Okay, even if you then convert it into a heat signal, this signal arises from ionization.
Okay, and so you lose the others.
And so you lose the, I mean, to me, you lose the motivation to go for cryo detectors, because then you have again the problem, well, not the problem, you lose a lot in the nuclear recoil energy threshold. And also, even if you know what is the quenching factor, but then this means that you maybe rise the threshold by a factor of 5. So this is good, for example, to do dark matter with electrons, but not, in my view, to dark matter with a nuclei, because it's at the uncertainty of the quenching factor, the complication of a cryogenic experiment, the small mass of a cryogenic experiment. So to me, it's difficult to see how we can compete with liquid scintillator in the low mass region, for example, like dark side S2 volume analysis or things like that.
Okay, but is there any way a proper voltage, maybe an intermediate one, where they can use both channels, because they show this very good separation?
Yes, but I think that the good way is the better way is this one. So in this case now I did not delete the setup, but what they do is that they have a small voltage, as you say, so that you don't have this, so you don't have this part that dominates. But but the ionization is read independently.
Exactly. Okay.
So it's not that you exploit the conversion of ionization to heat. So here you have one sensor, with one amplifier for the ionization, which is an electrical signal, and then they have the temperature readout, which are independent. While CDMS does not do this, because they always convert into heat. They don't have. Are you sure? Yes, I mean, so you can read the ionization, but the heat is always the point is that the heat is always biased by the heat, by the ionization.
Okay, continue.
So superconducting. Okay, so just so we as particle physicists.
There is a question.
Yes. Using only the heat, we have to wait 4 seconds for each reading. Using also this ionization signal, how many times we have to wait?
No, this does not change the thermal response, does not impact, because it's something, it's much faster. So this means that you have a high energy release in the crystal, and then you go with the thermal signal as without. Okay, so now we move to superconducting devices. So let me just introduce a bit of superconductivity, because it's something that we as particle physicists have maybe never seen or simply forgot. So let's start from the basics, so about the Drude model with the Drude model of conductivity. So as you know, the current density is proportional to the electric field, and this is a function of the mass of the charge carrier, their density and charge. But now I would like to put the accent on this tau here, which is the mean free time between collision with phonons. What does it mean? As you know, when you have conductivity, you apply the electric field, but the electrons scatter with the lattice. And this means that they don't have, so there is a mean free time in between the scattering. This is something that lowers the superconductivity of our system, because if the electrons would be free to move in the lattice, then you will have much higher conductivity. So this tau would go to infinity. But this is something that therefore limits somehow the conductivity, and this is why we have resistance in our metals. But so when we say with phonons, this means that in this impact, basically this causes lattice vibrations. Now, this is this movement again is also is driven by temperatures. So this chaotic movement of the electron depends on the fact that we are at 300 millikelvin. And what happens is that when we lower the temperature, so the energy is not enough to excite these phonons of the lattice. And therefore, below some critical temperature, which depends on the specific metal that we are considering, we have the emergence of this phenomenon of superconductivity, in which we have zero DC impedance. So how does this work? So the idea is that the electron cannot collide with the system because it has not enough energy in order to excite it. But when an electron passes through a lattice, then it will cause a small deformation of the lattice, because the electron is negatively charged and the sides are positively charged. So you have a small deformation. So when this electron goes away, then you have some excess positive charge in one part of the lattice. So this excess positive charge causes another electron to come being attracted by this. So there is this long range interaction, because this goes away, and after a while this one arrives because it is attracted by this deformation. There is this long range deformation, which is hundreds of nanometers, so several sides, between a couple of electrons within couple of electrons. One thing that we have to understand is that this phenomenon cannot give to a net current in some direction, because we don't have a generator. And therefore, these two electrons necessarily needs to have opposite direction in order to have more momentum. So these two electrons are somehow bound by this deformation with a very small binding energy. This is 0.4 milli-electron volts in aluminum, which is one of the most common superconductors used. And these two electrons with the opposite electron spins forms a post-condensate. The fact is that you have to think is that it's not that these are really couples, because they are couples, but they don't last that much. So they are couples for a while, then they change and they couple to another one. So it's a system of coupling between all the electrons for a small amount of time. So this gives then something that is a coherent state between all the electrons, which are linked by the lattice size by this phenomenon. And therefore, breaking this coherent wave of wave function of all the electrons is extremely costly for the system. And so this does not happen. And therefore, the electrons live in this system of Hooker pairs which do not collide with the lattice, and can move freely with zero DC, so direct current impedance. So superconductivity is very common. Here, this is just a table taken from Wikipedia, in which you have all the elements which undergo naturally superconductivity when we lower the temperature. For example, what we use in our fields is for sure aluminum, which has a critical temperature of 1.2 Kelvin. Below this, we have superconductivity. Then hafnium also, indium, molybdenum, niobium are used to make devices, all of this. And then there is, of course, alpha tungsten, which is the one used by the Crest experiment. We also use titanium. Sometimes you see basically the majority, not the majority, a large fraction of metals undergo become a superconductor below some temperature. The point is that then you also have to look at the temperatures. They are always in the Kelvin range, but some of them is very low. The point is that we want superconductivity in, well, mostly not to make detectors, but to make magnets, okay? Because of course you can then have a high currents without dissipation. And therefore, our colleagues on solid state are trying to look for something simpler than cooling at helium temperature, so 4 Kelvin. And they also try to engineer artificial superconductors with a higher transition temperature. And one of the more promises this IPCO, which basically is a superconductor at above the liquid nitrogen temperature of 7 Kelvin, and therefore it's easier to operate simply because nitrogen is cheaper than liquid helium. So let's start with the TESs. So a TES is a transition edge sensor. So the working principle is similar to that of the NTD. So again, I said we want this device to convert the temperature variation into a resistance variation. But as said before, the range of values of resistance is completely different. Here you are in the million or down to also micro-ohm when you have small changes of signals. One parameter which tell us well, one step back. So how this system works. So this is a tungsten, so something that has a transition temperature of below 20 milli, but then depending on how you engineer the superconductor, you can tune this transition temperature. Oh, sorry. So you are here, so this is the superconducting state in which you have zero resistance. And this is the normal metal state in which you have the resistance of that metal. And so you have, when you lower the temperature, you have the transition from metal to superconducting. And so, and this is the working principle of the TES, that you stay on the edge of the transition, so that a small temperature change causes a large resistance variation, which is actually what you want to measure. Indeed, for TESs, but also for NTD, we are used to look at the response of the device as this logarithmic sensitivity, which gives you basically what is the relative variation of resistance with respect to the relative variation of temperature. Say you have for 1% variation of the temperature, you have 10% variation of the resistance. This is the meaning of this alpha. So the point is that in order to read these small resistances, this is very difficult because it's not like reading mega ohm or giga-ohms. And this means that in order to achieve the best sensitivity, we also have to use sophisticated amplifiers. And in particular, they use these systems, which is a squid circuit, which is a superconducting quantum interference device, which I will not go into the detail of this system because it's very complicated. It deserves hours only to explain it. But the idea is this one. So this is the resistance of the TS. So this is what we want to measure. We put in parallel a shunt resistor. So this is just to give some feedback to this resistor. And so this means that when the resistance varies, since this shunt resistor is of the same order in this case, so it's similar in value to this resistance, you also, since it's a parallel configuration, this resistance changes, therefore the current split in a different way when this resistance changes. So you have also current variation on this arm. And this current variation is converted into a magnetic field variation through this inductor. And a squid is basically a device that can measure magnetic field down to the quantization of the magnetic field. Okay, so it's basically it's the most sensitive magnetometer that we have. Again, down to the quantization of the magnetic field. And therefore, the idea is to use this squid, which is this device here, in order to sense the variation of the magnetic field in this inductor, which is due to the variation of the resistance, with the squid itself. This is complicated, but it's very low noise and brings you the record damage resolution and threshold of cryo detectors. So this is again a thermal signal, so maybe then this means that the time development that you also asked before, the relaxation time depends on the capacitance of the system, heat capacitance of the systems, and conductance. So the conductance you have to think is as a 1 over the resistance, thermal resistance. So in thermal circuits, we don't use thermal resistance, but we use conductance, which is 1 over the resistance. So this is the time constant, like RC of the system. And so the larger is the device, the slower is the device. So in the case of quarry, we have seconds. Here we have 100 of milliseconds, but only because the device is smaller. And so when you have these cryo devices, then when you engineer your sensor, you have to take into account all the thermal system, and this is something that gives you the example of this. So, for example, you have to take into account the system of the crystal, which has the temperature and this capacitance. Here is the heat path, which can be think of the ground of the system. And then you have the conductance to the bath directly from the crystal, but then you have the sensor, and the sensor which is attached to the crystal has its own capacitance and its own conductance at the same time. So in order to model the time development of the signal, you should solve this circuit here, which is often impossible because you don't know the value of these conductances mainly. You cannot measure them independently, so it's something just that you know the number of poles of the system, and that's it. Examples. So the successful application of TSS in particle physics is mainly in the field of dark matter, in particular again for this process that you've already seen many times. So the elastic scattering of dark matter of target nuclei. The point is that these devices, as said, are good for low energy threshold, but since the volume is small, and they're really small, so these devices compete only in the search for light dark matter. And okay, so this is so we want to use cryo detector because they can reach very low energy detection threshold. However, we have the problem is that since they are difficult devices to operate, that scaling up the mass is quite a challenge. So one of the successes of this application of cryo detector to particle physics is the CREST experiment, which operates at Gran Sasso Lab, in which they have a crystal, in this case of calcium tungsten, and this is the advantage of cryo detectors, because as said, you can choose between, just simply choose the compound that you want based on the physics that you want to observe. In this case, they wanted a detector capable of sensing different wind masses, and therefore they choose this compound which has tungsten, which is heavy, 180 for heavy winds, calcium 40, and oxygen 16 for light winds. Now they are focusing only on light wind, but at the beginning they wanted to go also to large range of wind masses. And this is made of a crystal, which is again quite, this is in this case is around 300 grams. With and this is the sensor that you see is directly lithographed on the surface of the crystal. And the idea of the detector, which is quite common also in Super CDMS for TS, instead of having a tungsten TS, so the sensor, which is this small part here, and then to have a phonon collector. So basically the phonons, which you have to think as marbles, which scatter in the crystal, are absorbed by these pads, which then are in somehow vehicled to this sensor in the center, where they cause the temperature increase and the development of the CD. Another application is the coherent scattering with the nucleus experiment, because again, this comes for free, because just the application of this, the very same device that we have for dark matter, 2 neutrinos, because with these devices were developed for nuclear recoils. Since with this process we are looking for nuclear recoils, this is exactly the same observable. And therefore, we also started applying these devices to neutrinos with the nucleus experiment, where, again, as in the case of the ricochet experiment or the CONUS experiment, as you have seen yesterday, you have a source which is a nuclear reactor, neutrinos on the crystals. But what is nice of this is that we are aiming at the sensitive neutrinos with only 10 grams of detectors, thanks to the high sensitivity of TSs and to the high cross section of the coherent scattering because of the coherency. And this is possible because, again, this is the target uses tungsten, therefore the coherency is largely enhanced because of the high mass of the high number of nucleons of the target. And here you can see that this results in which you have very low energy threshold. And now we are in the phase of taking the apparatus to the nuclear power plant.
So it's the same material as crest?
Yes.
As a crystal?
Well, yes, the original material is the same, calcium tungsten. Then crest is moving to sapphire or silicons to lighter, because of course this is there where they are more competitive. In the case of nucleus, we also consider the sapphire, but now we are discarding this because basically sapphire has the atomic mass is too small, and we realize that we cannot go above the background with that. So we need a higher cross section, so we enhance the coherency, and therefore we need the tungsten, and therefore we go with calcium tungsten. One problem of the field, in particular for dark matter and neutrino scattering, is the fact that when you go to low energies, we started observing a background of unknown origin. So this means that here you have the experiments, some of the experiments of the field, in which, to make it short, from our Monte Carlo simulation, we expected a flat background down to threshold. So you expect to have something which is flat. However, the majority of the experiment with one exception, just see something that increases towards threshold. And this is true both for above ground experiment, like nucleus, and underground experiment, like crest. And these are experiments with a shield which is in between nucleus and crest. But what you have is that you have this sharp rise here that is not explained. And this is a great limit for the experiment of the field, because irrespective of how good you are in lowering the threshold, because this is, so you can say that yes, the TSs are very good because they have very low threshold. All this effort is useless because you do not do physics with such a high background. Okay? So, for example, the CREST experiment put a limit which on the detection of WIMPs, which basically is as if the threshold is 200 electron volts, because they have this rise of the background here. So this is the problem. This goes under the name of the excess, because we have this excess and unexplained background. And we hosted in Rome a workshop on this excess problem. And to tell you how diffuse it is, we were about 80 people talking about this excess background. So this is shared among different experiments in the community. The tendency is now to think that this is due to some solid state effect. For example, phonons, which are not created by particle interactions, but phonons which are created by, for example, friction of the crystal supports on the crystal itself. So because of the cool down, there is some contraction of the system, and this there's some friction of the supports which create phonons, which can create signals that can mimic particle interaction. The point is that when you go to threshold, then also doing some pulse shape discrimination is very difficult, because the signal to noise ratio is small, and therefore also spotting small differences in the pulse shape becomes very difficult. Okay, so this closes the DC superconductivity. So if you have questions, we can collect them now. See?
Or maybe I missed one part, but how can you be sure that maybe not possible, but how cannot you be sure that it's a signal, for example,
How can you be sure that that is a signal? But what do you mean it's a signal? So, okay, whether it's a dark matter signal?
Maybe.
Okay, the point is that yes, of course, you should always remember that you're looking for a signal. But the point is that you don't observe the same between different detectors. So this is one example. Then you have other detector, and they measure a different excess. And so, for example, if you have an other detector with higher threshold, you will have an excess also towards higher energies. Every detector has its own excess. So something that is not really.
It's not compatible among the various.
No, it's not compatible among various experiments, but not even, it's not compatible in the same experiment. So if you use two identical crystals, you operate them, you obtain different excesses. Okay.
It was called thresholdino.
Thresholdino, by boom.
I think it was Marco Cirelli.
Thresholdinos, yes.
You said that almost all of these detectors have shown this kind of problem, but not all. Why?
Now, this will go, this is the last one, which is, will, in this case, we don't have the excess, but still we are operating this device on surface, so we can say that we don't have the excess on at this background level. But when we will lower the background with the shields or going underground, we don't know if we will observe the excess emerge or not.
Okay.
Okay. Okay. So last chapter, which is AC superconductivity.
We have 40 minutes, including questions.
Okay. Okay. Yes. We okay, I have the formulas that disappeared. Questa pagina. Okay. There is not much to do. Okay, so we have just to the point is that we have the conductivity. These formulas are alive. So basically, was here, and if you think again to the Jude model, so the conductivity was basically the DC conductivity, meaning that this put the current as a function of the electric field directly without any imaginary part. And so this is the conductivity that you have from the simple Jude model.
So,
Now,
sorry, Marco, if you look at the slides on Indico, the formula is there.
okay. So, but the point is this, is that when you, for example, what happens when you apply an AC field? So you have that waves move the electrons forth and back. So you still have the collision, but what you have is that since the electrons have their mass, when you change the sign of the electric field, they take some time because they have to break, then turn and go in the other direction. So they have some lag. It's not that when you change the sign of the electric field, the electron immediately change direction. It has to slow down, rest, and then change direction. So this is a lag, okay? And this is a lag, so this a lag, if you remember, can be seen as an inductance, okay? So as in the case when you have the magnetic field generated by the inductor, if you change the sign of the electric field, then you need some time in order to discharge a magnetic field and recreate the magnetic field. And this creates a lag in your circuit. So this means, more formally, a complex impedance which depends on the frequency. So this lag, which is due to the fact that the electrons take some time to change the time and to change the direction and follow the electric field, is something that happens also in a normal conductor at room temperature. The point is that this lag depends on the on this time, which now we do not see because the formula not here. This on the time that you have between two collisions. But if you are sufficiently fast in changing the direction of the electric field, then you are able to see the electron basically freely moving because you don't see the collisions, and then you can see this lag, because otherwise this is cancelled by the impact on the centers. But so in normal conductors, this lag appears only at very high frequencies, because this tau is very short, and therefore you have very small time scale, and so this appears as 16 terahertz, which is something that where we don't have electronics, so we don't care about this phenomenon. However, in superconductor, what happens is that this tau, since you never have collision, goes to infinity. And therefore, you have to any time to observe the movement of the electrons. And so even at low frequency, you can see this complex impedance. So you do see this lag of the electrons because we don't have the collision. So we, at low temperatures, we have that the DC impedance is there. And you do only have the imaginary part of the conductance. So now let's try to understand what this imaginary term is in terms of conductivity. So the impedance, so we have this sigma here. So the impedance is the length of the conductor divided by the area divided one of the conductance. So you put this formula here, so you get something like J omega something. Okay, and if you remember, J omega something is the impedance of an inductance. However, this inductance depends on the mass and on the charge and density of the charge carrier. So this is not related to the inductance that we are used to, which is those created by the magnetic field due to the geometry of the conductor. If you have a wire, even if it's a straight wire, you have the inductance of the wire, if you remember, which is due to the magnetic field that the AC movement of charges create around the wire. In this case, this inductance, the energy which is stored in the magnetic field in the normal inductance is not stored in the magnetic field, but it's stored in the kinetic energy of the electrons, which moves in the conductor. So this is due again to the inertia of the electrons, which takes some time to move, and they store energy in their kinetic energy. So exactly the same of the magnetic inductance, but this is due to the movement of the charge carrier, and therefore this is called kinetic inductance. Does not arise in normal conductors because we can see it only at the frequencies, but in superconductors we see at any frequency. So you can also play with the formulas, and you can also compute what is the energy which is stored in these charge carriers. And again, the formula is exactly the same as the magnetic inductance. So an inertia which is called by energy reservoir, which is not the magnetic field, but is kinetic energy of the charge carrier. So let's go into the model. So now, if you have superconductor, typically you can model this system in this way. So I said we have that when we go to low temperature, the electrons will be bound into these pairs, which are called Cooper pairs, but a small fraction may not be bound in Cooper pairs. So the point is this, so therefore we can model this conductor as in this way. So this is the wire, and then when we enter the wire of the superconductor, we have two systems. One system which are the few electrons which are not bound into Cooper pairs. So this is normal metal. And then we have the part in which the other fluid, which are the electrons which are coupled into Cooper pairs. So if you are with a DC signal, it's not a signal, with a DC current, of course the current will entirely flow through the path where you don't have resistance, because of course there is no mean to go through the resistance. So this is a superconductor, because even if you have a resistance, this resistance is in parallel, so the current does not flow in this resistance. But if this current is not DC, but it is AC, this part of the superconductor has this inductance, which is the kinetic inductance. Therefore, the overall impedance of the wire is the zero the impedance of this fluid here, which is the zero impedance of the Cooper pair resistance, plus the inertia term of kinetic inductance in parallel with this resistance. So this is the full impedance of a wire, superconducting wire. When you have, again, when you have DC current, this inductance does not arise, because the inductance only applies when you have alternate current. And therefore, we have zero in parallel with this resistance, and therefore the impedance is completely zero. But when you have a AC signal, you do have this, therefore the superconductor both has inductance, but then you also see the resistive terms, because these are in parallel, because this is no longer zero. So if you do some simple math, we can convert this into this, and therefore you can also convert it as a series of resistance. So this is the AC case, the series of resistance, the kinetic inductance, and the normal magnetic inductance, which is a property of any metal, of any conductor, and this depends on the shape that we give to that conductor. So based on this, relatively recent times, so the new kind of detector was proposed, which are the kinetic inductance detectors, which were invented by Professor Jonas Smudinas at Caltech in 2003. So the working principle is this one. So these are not actually real calorimeters. So the idea is that of having a superconductor cooled at very low temperature, below the critical temperature. So in this case, we are not lacking the TS on the edge of the transistor. So now we are using superconductor for what it is. So very staying below the transition temperature. And but for example, if you take aluminum, which is 1 Kelvin, we operate them at 100 millikelvin, so much lower than the transition. So the idea is that we can, since the inductance, let me take the formula. Where is it? Okay, since the inductance depends on the number, so this is the inductance, depends on the number of charge carriers. The idea is that of changing the density of charge carriers so that we change the inductance. So in order to change the number of charge carriers, we can break the Cooper pair, and this can be done by photons or phonons. Therefore, if the photons or phonons are absorbed as superconductor, we change the number of charge carriers. So this means that then the kinetic inductance increases because we have less charge carriers, and also that we have the equivalent resistance increases given by the parallel of this. Therefore, a change of the density of Cooper pair is converted to a change of the resistance and the inductance of the superconductor. So how do we measure inductance changes? So the idea is to use resonators. So possibly the best resonator that you know is a pendulum, in which your observable is the frequency of the pendulum, which depends on the length and on G, length of the pendulum. But we can build also resonator with circuits that you know very well, and one resonator, the resonator is the LC resonator. It's a natural resonator. So you have the frequency, and in this case you have that the two energy reservoir. One is the potential energy of the ball, and the other one is the kinetic energy of the ball. And you have you can see this as a continuous movement of energy from potential to kinetic energy. So this is the oscillation potential kinetic. And in this case, the oscillation is between the energy stored in capacitor and the energy stored in the inductor. So here you have a capacitor, inductor, in terms of energy. However, there are dissipation that even if you excite the system, does not let it go forever. In the case of the pendulum, the dissipation is the air friction, and in the case of the circuits, is the parasitic resistance that usually you have in all wires. So, in order to assess the quality of resonators, we define this quality factor, which tells you basically which is the amount of number of cycles before the amplitude of the oscillations drop by a factor 1/8. So, and what is, when I was preparing this lecture, just for curiosity, was what is the quality factor of these two systems? For example, if you take a LC resonator at room temperature, it's very you can get quality factor of 10 to 100. So this means very few oscillations that you can have because of the parasitic resistance. But if you take, for example, a pendulum of the 17th century, you can compute quality factors up to 10,000. So circuits are very bad resonators because compared to a pendulum because of the parasitic resistance. Of course, since we want to measure inductance, and we measure our observers the frequency of oscillations, the more cycles we observe, the more precise is our determination of the inductance. And therefore, we do want a high quality factor because we want to measure several periods to assess with precision the inductance. So, therefore, the idea behind the kinetic inductance detector is that while we at the first year of physics, we were using this system in order to measure G through the frequency of oscillation. Now we want to use this system through the frequency oscillation to measure the inductance. Of course, the point is that the problem is this parasitic resistance, but if we go with a superconductor, we don't have the parasitic resistance, and therefore we can reach much higher quality factor. As we will see with superconducting resonators, we can reach 100 to 1 million, 100K to 1 million quality factors, so even better than the pendulum of the 17th century. So just to remind you, so this is the typical readout of an electrical resonator. So you excite with a wave, and then you read the signal at the output of the circuit, and therefore your signal at the output of the circuit is a function of the quality factor and of the frequency of the generator. So we have therefore our objective is we send a wave, then here we have the impedance of the resonator, and we are looking at the wave at the port 2 which is the wave which is transmitted past the resonator. And therefore we want to see how, by changing the inductance, we see a change of the wave here, because we know what we injected and we measure here. So what happens is this. So this is the wave transmitted past the resonator as a function of frequency. When we have an interaction, we have, we say, an increase of the resistance. And so this means a lowering of the quality factor. This means that the depth of the reference goes up. So it's lower. Therefore, if we bias the resonator at fixed frequency, what we see is that the amplitude of the transmitted wave increases when we have a particle interaction. This is because the resonator goes out of tune, because it's moved away. No, in this case, it's not out of tune, sorry. So in this case, you have that the depth of the resonance is lower, and therefore the resonator absorbs less the wave and transmits more the wave. So we have amplitude increase. Then, for the variation of the kinetic inductance, what you have is that you also have that since the resonator goes out of tune, because you change this one, you have a change of the phase of the wave transmitted by the resonator. Therefore, we have an amplitude modulation and a phase modulation. And this is exactly the same system of readout of the radio. So you have AM and FM signal. So amplitude modulation and frequency modulation. Indeed, we use hardware which is derived from radios to read these systems. So yes, these are signals from our kinetic inductance detectors in which we compare. So this is our resonances at a frequency of 2.6 gigahertz. So Wi-Fi band. So these are the same electronics that we use for cellular phones or Wi-Fi. This is also the pro of this technology, because you can use commercial electronics is very well developed for industrial application. With a quality factor of 150K. These are typical signals in phase and amplitude modulation. And in this case, we are a bit faster than other cryogenic detectors. Basically, because we are off equilibrium. We are not thermal detectors. We are just seeing the change of density of Cooper pairs generated by interaction. So it's not related to the temperature of the system. So so if you want to go with best sensitivity, you should use a transitional sensor. But if you want to go with a large number of sensors, you should go with kinetic inductance detectors. Why so? Because basically this is they bring a natural multiplexing capabilities. Because the idea is that you can couple to the same feed line several resonators, and how you can distinguish them very well. They are almost identical, but you change one of these parameters from the resonators. For example, you can change only the capacitance, and this will give you a different resonant frequency. So this is an array of kinetic inductance detectors, which only one wire which runs into them, and this is the frequency scan. And as you see, while we scan the frequency, each of these depth is a single kinetic inductance detector. So in this way, we have all of them coupled to the same feed line, and we can read them in parallel. Up to 1,000 kits have been deployed by and coupled to the same feed line for readout, and this is extremely helpful, in particular in cryogenic detectors, when where the scale up of the sensor is difficult. So how much time do I have?
So it's 20 minutes.
20 minutes, okay. Good. So yes, this is what I was saying. So why we should use kits? So they are easier to fabricate than TSs. They are not a purely thermal detector. They are off equilibrium detector. Therefore, are more insensitive to vibration in general, to temperature instabilities, to electromagnetic noise, because these are AC devices. So we are not a DC where there are much more noise from the electronics. And why not? Because the sensitivity is worse than TSS. At minimum, it's 2 times worse, but in most applications, it's 5 times worse than TSS. So yes, for a large number of sensors, not for sensitivity.
Sensitivity, you mean threshold or you mean
Let's say it's threshold, yes.
energy resolution?
It is the yes, it's the threshold. The energy resolution is another story. This depends more on the, but here we are talking about threshold.
Okay.
Now, kits in particle physics. So at the beginning, the kits were proposed to create light detectors to be applied to the core experiment. And this is why kits, because we have to deploy 1,000 of detectors. But then we moved and we are now starting to apply this to the dark matter and the neutrino field. So what is the point? So this is again to go better into the off equilibrium signal. So this is so imagine we have this substrate of silicon, which is silicon because it's a common material, not because it is a semiconductor. So we are not using it as a semiconductor. And we have the kits deposited on the surface. Then you have some particles, photons in this case, which interact in the silicon and convert into phonons. These phonons are not yet temperature carriers. At the beginning, they are just vibration, and these are called athermal phonons. And so this is just like when you hit this, and then you have it moves also here. So it's just a vibration that propagates in the system. And this is what we detect. So these are like marbles that scatter in the crystal until they reach the kit, they break the Cooper pair, and generate a signal. So what we have to be good is to try to collect the majority of these photons, like with the problem that we have with photon multiplier. We want the collection efficiency. And this was the first part of the R&D. Everything started in using kits as particle detectors in 2010, when in France they first observed cosmic rays interacting matrices of kit that were made for CMB. Then at Caltech, back where they invented this sensor, they also started to propose these kits for particle detection. So again, using this phonon mediation. So phonon mediation means that the particles are absorbed by the substrate, which is silicon in this case, converted to phonons, and then are the phonons that create the signal. So there is a medium carrier, which are the phonons. And so they started also in Caltech, where they first obtained the first energy resolutions and of 380 electron volts with kinetic inductance detector. And then in Rome, we started a project where we improved by a factor of 10 this value from 380 to 25 electron volts energy resolution. And this project took about 5 years to improve by 1 order of magnitude the energy resolution of these devices. And these were made intended as light detector, in which all the sensible part is this square silicon that you see, and this is a single kinetic inductance detector put here. And then to do the parallel, several light detectors, the idea is to put several of them in parallel, and then you can read all these light detectors. Questo sta sempre qua. Come si fa? Altro?
Nascondi Controlli riunione molto.
Okay. So, then we started to also to move to neutrino dark matter field, meaning that we made them not just a wafer of silicon, but a bit more bulky. And this is an example of how they interpreted this in Grenoble, which is very nice. The idea is to have, they developed a Wi-Fi detector, but this is truly Wi-Fi, because since we are working at radio frequencies, we can implement this. So what they did is that to have this, this is the crystal absorber, then there is the resonator on top of it, but then the wire that sends the resonator is decoupled. And simply there is an inductive coupling between the feed line that we use for the readout and the crystal absorber. So we have no direct wiring between the absorber and the readout. So this is a Wi-Fi kit, which is a very nice approach because they in principle let you change this as much as you want, but there's some drawbacks because because of vibrations, which are natural in these systems, you have that the distance between these two changes, and this means also the capacitance and inductance change, and this adds a lot of noise. So now this is a bit limited by this, but if you have in mind some experiment which might need some Wi-Fi detector, so that you don't have to wire to, this is a way to do it. And
How thick is it?
so this is 3.6 times 1 centimeter, so this is a roll.
And thick.
Perché non so questo? Okay. Okay, then at the INFN, we propose a new way to exploit the multiplexing capability of kits, so to realize a new dark matter and neutrino experiment. And the idea is this, again, so this is not new, but that to have a cube where you have, which is the particle absorber, where particles interact, create a thermal phonons, scattering the lattice until they reach the sensor where they generate a signal. In this case, the sensor is a kit, but in order to exploit the capability of deploying a large number of pixels, we needed to do some bulky absorber. So we took this thick silicon wafer, because this is no longer a wafer because it's 5 millimeter thick, so it's like a burger more. And we carved this, but the carving are not complete since they leave intact a common disk on the opposite side of this picture. And then we flip this wafer, we have an entire surface where we can do the lithography of the kits. Here is a matrix of 60 kits, which are all multiplexed and connected together. In this way, we can deploy 60 detector independent cubes, not independent, 60 cubes together with a single readout of 60 pixels in parallel, which is a great improvement in the scale up of number of detectors in cryogenic environments. So the nice thing is that in this way we can also have a fully active detector. So this core here is fully active. We don't have inner part and we don't have the supports that, if you remember, was a problem for the excess. So we have the supports that are supposed to by friction to create events in the crystals. In this case, everything is active, and therefore the supports are here, but this is not a part of the detector that we use. And so thanks to this, so we can use if we observe the screen line in one kit, we can use the surrounding dice as vector. And indeed, if we do this, this is what in a normal experiment would do just by the energy spectrum that you observe. But if you, just by looking at the energy spectrum that you have here, but if you veto the signals with the signals like these ones, it's clearly you see that the majority of the energy deposit is here, and here we have some leakage. If you veto this, then you have a very nice flat vector. So the point is this, that this part here is not an excess because this is compatible with the noise false positive rate. So in our case, at least at this background level, we don't observe excess events. So this is just due to noise false positives.
Say it again, what's the reason of the steep increase?
This one,
Yes.
oh, this is since we are very close to the threshold is very low. Sometimes the trigger spikes on noise spikes, and so we have a spectrum estimate of these noise spikes, which matches this one, and so therefore this is not excessive.
So not physical events.
Not physically, no. This is just it's just the tail of the Gaussian at 6 master that sometimes gives you a large event,
Large enough.
large enough. So, and with this I conclude. So, following this, now we have been approved a new experiment, and the idea will be to stack several of these wafers in order to create a volume which is fully active again, because here these are all silicon, which is all instrumented, and we could now have some fun, maybe as they do in the liquid scintillating detector, in fiducializing this volume or lowering the background, and we hope that we will not have the excess even when we will go to lower background environment at Grand Sasso. For now, the physics run of this experiment that should have this sensitivity in the low wind mass region is expected to be in 2027. Thank you.
Yeah, thanks, Marco. Thanks a lot for this very comprehensive and not easy but clear presentation. By the way, I went back to some of my nightmares at the second year of electromagnetism. So thanks for bringing me there. Questions? All experts in cryogenic detectors.
Superconductivity.
Superconductivity.
Maybe a small question. At the beginning, you said that helium-3 is a problem with cooling and that it's expensive, but is it lost? And
No,
how
it's
much
not.
do you
No,
need?
no.
Like you said,
It's not lost. You need so no, the point is this, is that it's not lost because it is in the circuit, it stays there. So the leakage is very small, maybe no, few percent per year, I would say, and less. The point is that you might need a lot, maybe 20, 30, 40 liters, depending on the volume. Okay?
You can sell it again afterwards, right?
If your institution allows it, yes, our does not.
Thanks.
I have a question. I was discussing it with your students yesterday at first session. Are you foreseeing any additional shield or filter?
Yes, here it's not the case because I mean, the focus was more detectors rather than experiments. But yes, so the idea is to have so this is the core outside. We might have a baseline option is to have a copper shield at cryogenic temperature. Improved would be to have a veto made of scintillating crystal lit by the detectors. And then outside we will have passive shielding with polyethylene leg. And this should be sufficient to bring us below then to the -1 values.
Can you also think to put it in a liquid? Is it easy to?
Like for example, Cosinus made these, so the guys that in the water Cherenkov shield. So yes, you could put it in a structure like this, or yes, you can use that. Yeah, that would be a very efficient way to lower the neutron background most of all. So yes, but it requires another infrastructure that needs to be realized.
So any other question? Maybe also on the lecture of yesterday. Okay, if not, we thank Mark again. In 5 minutes, we can have the coffee break upstairs and we convene here at 11:15, as usual, with liquid scintillator detectors. Una delle segretarie
Ho incrociato Roberta, e gli ho dato tutti a sulla ricerca dei taxi, ho prenotato il taxi per oggi, sì,
Ok,
dovrei aver
benissimo.
c'è il sì, mouse, il pointer, oppure
Sì, sì, c'è. Vedo le cose precedenti.